Alright, so today today I want to talk about a insertion sort algorithm. Okay, it's one of the sorting algorithms in computer science. I'm not going to get into anything too heavy, nothing too deep. I'm just going to briefly introduce what it is, how it works, and I'm just going to quickly talk about its time complexity, although I'm not going to dive heavily into it. If you guys would like, I'll make another video on that topic alone. But for now, before we get started, let's make quick notes. Its big O notation, in worst case, is big O of n squared. Okay, this is because this is n squared on big inputs because of number of comparisons that it does and so on. And its best case is big O of n. Okay, this is for small inputs and or nearly sorted array. Okay, and another thing to note here before we get started is that insertion sort is very intuitive because it's very close to how us humans would sort a, for example, deck of cards or anything of that nature. So let's work through an example and you'll see what I mean. Suppose that we have an array called A with the following values: 5, 6, 1, 3, and 4. Alright, I'm just gonna keep it nice and simple, otherwise it becomes too tedious. So this 5-element array is good enough for explanation. And please note that I'm starting the indexes at 1 instead of 0. Okay, don't forget that, otherwise you will be confused. Okay, just for the purposes of this video. Alright, so brief overview of what insertion sort, how it works is that imagine there's a line right here to start with between the first element and the second element, and the insertion sort starts at index number 2. Okay, this is because the first index, there's only one element in that value. I mean, there's only one element before the rest of the array, so it's already sorted. I mean, one element itself is already sorted, and it has nothing to compare values with except to itself, so it doesn't make sense to start at 1. So therefore it starts at index number 2. Okay, and the way it works is you take the value in the index number 2 and you can compare, let's just call it k for key, and you compare that key value to all the previous values before it until you encounter a value which is smaller than the key. Okay, so let's walk through an example. And if the key is smaller than the value that you're comparing it with, you just swap the values. Okay, so in this case, the insertion sort algorithm starts, and it says that we have a value of 6 at index number 2, and it compares 6 to 1 before it, which is 5, and it asks, is 6 less than 5? No, it's not. So the new array becomes, I'm just going to walk through step by step here. Okay, 5, 6, 1, 3, and 4. Okay, with the same index numbers, 1, 2, 3, 4, and 5, with the line moved to here. Okay, now everything to the left of the line is sorted, and everything to the right is considered unsorted. Okay, so now our key is at index number 3, which is 1. Alright, so it takes that number and it compares it to 1 before it, which is 6. Is 1 less than 6? Yes, it is. So we swap these values. Okay, sorry for this. Okay, so these values get swapped. So now we have 1 here and 6 here, and you keep going, you don't stop there. So is 1 less than 5? Yes, it is. So we swap these values. Okay, so this is the basically the entire algorithm. You just keep repeating this until you reach the end of the array. Okay, so then 1 comes here and 5 comes here. Alright, so, and then a line gets shifted, but we're going to create a new array to show that, to reflect that. So a new array A will be 1, 5, 6, 3, and 4. Alright, with its index values just to keep the persistence. And our invisible line is going to be here now. Okay, now our new key value is 3. Okay, so that's our key K. We compare that value to everything else that comes before it until you encounter a value which is a less than the key. So in this case we have 1, so we stop there. Alright, so what happens? Well, we compare 3 to 6. One before it is 3 less than 6. Yes, it is. So we get rid of it, and we swap the values. Okay, I should get a better eraser, but it's okay. So 3 comes here, and 6 comes here, and then you keep going, repeating this algorithm. Is 3 less than 5? Yes, it is. So we swap. So then 3 becomes here, and 5 takes over in this place. Maybe I should use a different color than the one I'm using for indexes, but it's okay. So this is 5. And then you compare, we have one value left to compare. Is 3 less than 1? No, it's not. So we stop here. So a new array, just to keep this going, is 1, 3, 5, 6, and 4. Okay. With its index values the same as above. With our new invisible line right here. Now you can see why I chose a small array. If it was a bigger array than this, it would be too tedious to do this video, so we'll just stick with a nice and simple one. Okay, so now we have our key value is 4, and we compare that to one before. Is 4 less than 6? Yes, it is. So we swap them. Okay, so this becomes 4. Let me change it to green. So this is 4. Oops. Bad choice. 4. And this is 6. Okay, you keep going. So is 4 less than 5? Well, yes it is. It absolutely is. So we swap. So 4 takes the place of 5, and 5 takes the place of 4. Okay, so this becomes 4 here, index number 3, and index number 4 becomes 5. And then you keep going with this key value. You don't stop there. That's the key. Is 4 less than 3? No, it's not. So we're done. This is a sorted array. Let's just create a new array to reflect this, and we are done. So our brand new array is, as you've imagined from the beginning of the video, 1, 3, 4, 5, and 6. With the indexes 1, 2, 3, 4, and 5. Conceptually, this is all that is into insertion sort. Now, if you guys want me to post a time complexity analysis for this algorithm, please comment in the comment section below and subscribe.